Hello, everyone. I'm Patrick Mijula. I work as a senior data scientist at DeepSense AI in Bydgoszcz. And today I'm gonna show you our research project that we were working on in a group of 4 people from DeepSense between January and March 2020. This project is called Clothes Swapping. First, I'm gonna tell you what I mean by clothes swapping. I will describe the goal of our project. Then I will present an interesting related result from the literature. Then the main part of the presentation, I will show you our entire pipeline, the pipeline of our solution. And in the end, there will be a short time for a discussion. So what is clothes swapping? Assume that you find or take a picture of a person wearing a t-shirt you like. We call it the source. And you also have a picture of you, which you call the target. And we'd like to know if you would look nice in the same t-shirt. So the goal of the project is to transfer the t-shirt from the source onto the target person. And bear in mind that we only have those pictures. We do not have any metadata regarding the cloth on the poles, just the 2 pictures, just 2 sets of pixels. And how to do that? Before I will show you our solution, I'd like to present one of the interesting approaches that you can find in the literature. This is a work of people from the Saarland Informatics campus, which was presented during the ECCV 20 conference in the end of August 2020. What they do is they re-render a human from a single image. In this way, they are able to transfer a cloth to a person taking any position. It's very impressive. However, there are 2 details. The first one is that they work on small pictures, and the second one is that they work on plain clothes, on clothes without, patterns. And we place attention uh, on those 2 points. So we would like to work with arbitrarily large pictures and with clothes with arbitrary patterns. And this is our pipeline. It consists of several steps with several models. We used mainly Deep Fashion 2 dataset to train the models. All right, so let's go through the pipeline step by step. Step 1, pose classification. In our 2D approach, we have to make sure that both the source and the target person are seen from the same side. There is no sense, for example, in trying to transfer a cloth from a person standing in front of the camera onto a person standing sideways. So we need a model that takes a picture and decides whether this is a front view, right side view, left side view, or back view. For this purpose, we used the transfer learning technique to get a neural classifier. First, we manually labeled almost 9,000 pictures from the Deep Fashion 2 dataset. Then we took the well-known ResNet 18 neural network and we replaced its last layer with a brand new one with 4 outputs because we had 4 classes, right? And we trained this neural network. We fine-tuned this neural network to get a good neural classifier. Step 2, generating masks and key points. For further processing, we had to extract body part masks, body key points, skin and hair masks, and cloth mask and key points from the pictures. We did it using 4 fine-tuned instances of the mask RCNN model. Step 3. In painting of hair and skin on source cloth. Sometimes we can see some skin parts of hair on the source cloth, and we don't want to transfer those skin or hair parts, of course. So what we need is to in-paint them somehow as a pre-processing step. We initially used in-painting function from the CV2 library to do so. It's very simple. It just looks for the closest picture, closest pixel outside the in-painting mask. As you can see, the result is not so beautiful. However, we had no time for anything more sophisticated, so we stick to it during our project. Once the preprocessing steps are done, it's time for two main steps. So step 4, key point transformation. We need to know where to transfer the t-shirt. All right, and the position of the transferred t-shirt is given by the transferred cloth key points. So we need a model that takes the coordinates of the source body key points, the coordinates of the source cloth key points, and the coordinates of the target body key points, and predicts the coordinates of the transferred cloth key points. To do so, we trained a custom 3-layer dense neural network from the scratch. We used a subset of the deep fashion dataset consisting of pairs of different pictures of people wearing the same clothes. Step 5, texturing. When we know where to transfer the cloth, we finally can do that. Our approach is as follows. We look for a projection from a plane to a plane having two properties. The first property is that it should project particular source cloth key points onto respective transfer cloth key points perfectly or almost perfectly. And the second desired property is that this projection should be regular. I mean, it shouldn't distort the interior of the cloth too much. Also note that this projection should be trained on the fly for a given pair of source and transferred cloth key points. Our first approach was so-called Delaunay triangularization. If you have a polygon formed from the cloth key points, then you can divide this polygon into triangles. And Delaunay triangularization is such a division which is optimal in a way that those triangles are as close to equilateral triangles as possible. So what we did was we performed the Delaunay triangularization on the source and transfer key points, and then we projected each triangle from the source cloth onto the transfer cloth in an affine way, which is possible then. But it turned out that the transfer cloth was too angular then. Also, whenever a part of the source cloth is, let's say, outside the polygon formed by the cloth key points, then it cannot be transferred. The second approach that we tried was training a small neural network on the fly. The first problem with this idea is that the training takes too long. And the second problem is that it turned out that a neural network is far from linear. I mean, even stripes become curved. So it's hard to train a neural network which will behave similarly to a linear projection. What we finally did was training a cubic regression on the fly. By the cubic regression, I mean the linear regression with additional features being combinations of x and y coordinates up to the third degree. We use some regularization from the third degree features to keep the projection as close to the linear as possible, and it worked well. And when we have a projection that preserves key points and is regular inside the closed area, then what we do is we simply project every coordinates inside the source closed area onto a pair of coordinates in the transferred area, and then we move the pixel onto the projected place. And in this way, we fill the transferred area with the source cloth. After the two main steps, we have two post-processing steps. Step 6 in painting. After transferring the source cloth onto the target person, parts of the original target, the original t-shirt wearing by the target person can be still visible. So our goal is to erase those parts to make the picture more natural. We did it using a GAN based on a paper Generative Image in Painting with Contextual Attention, which was presented during CVPR 2018. The last step, step 7, putting target skin and hair on transferred cloth. If there were some skin parts or hair parts on the target person, they now are occluded by the transfer cloth. So what we have to do is to put them back to the front. And we did it using simple manipulation on mask and pictures without any machine learning. So that's all about the pipeline. I'd like to also mention that I presented the pipeline on t-shirts. However, we did the same work for other cloth parts as well, for trousers, for skirts, and for short sleeve dresses. And some of the models inside the pipeline are cloth part specific. A short discussion. First question, could we do that better? Could we improve any part of the pipeline, or maybe could we modify the pipeline to get a better final result? Of course, we could, but it was what we were able to achieve under the time constraints we had. And the second question, will complicated pipelines like this one be replaced by super-duper GAN-based end-to-end models? We started this project with a super-duper GAN-based end-to-end approach, but we failed, right? Because it was just too hard for us or for a GAN to achieve. There are some problems like working with big pictures, working with patterned clothes, and so on. So I think that probably someday we will be able to get rid of such complicated pipelines and do such stuff end to end. However, not yet. Okay, that's all. Thanks for watching. And during the questions, I will run a live demo. So if you want to take part in it, then be my guest. And we will be able to get rid of such complicated pipelines and do such stuff end to end. However, not yet. Okay, that's all. Thanks for watching. And during the questions, I will run a live demo. So if you want to take part in it, then be my guest. And we will be able to get rid of. Alright, it seems I'm online right now. Okay, so first of all, I'd like to thank the organizers for inviting me to this conference. Actually, this conference is perfectly organized, in my opinion. You can even see me in the organized t-shirt, but it's an online conference, right? So it was sent to me. It's amazing. Yeah, this was my first sentence to you, and now I'd like to invite you to the demo I prepared for you. Let me paste it. All right, I've just pasted it on the chat, so you can use it if you want to. Let me show you how to do that, right? So I will share my screen. Probably I'm sharing my screen now. Is that true? Oh, it is. All right. So we can go to this close swapping demo link, and what we can do is we can do close swapping in the close swapping demo, right? So for what we can do is we can choose a source person, a target person from the file, choose the clothing type we want to transfer, let it be skirt, and click run, right? And then we can see some results. So this is the result of our algorithm. And what I propose to do then is to save it to your file and then go to the special community, that one, Patrick Mijua's demo, and paste it here. In this way, we all will see a result of your work. So if you want, then please try. All right, so let me do one more example. You can also use URLs. So let me show you such an example. Those are two random pictures from the internet. This time I want to transfer show sleeve top. Right, so this is the result. Yeah, so I hope we will see some of your result in a second. Or maybe we will not. The result is amazing, you say. Yeah, of course, those results are cherry-picked, so the result has to be amazing. Anyway, this is why I propose you to try on your own to and paste the result to check whether really the results are amazing or not. Okay, so I think it's the moment for the questions. I'm not sure whether I should ask the questions myself.
No, I will read them out loud so you can answer them. Okay, so the first question is from Bartosz Ludwiczuk. Bartosz asks, what part of the pipeline did take the most time to prepare? Data collection, learning, tuning the models? Patrick?
Oh, all right. Okay, I'm here. What part of the pipeline did take the most time to prepare? It's not so simple to answer since almost every part was hard and time consuming, and we did a lot of research and we tested a lot of approaches. What I can say is that the most my favorite part is this part with the point 4 or 5, I don't remember right now, this point on putting the clothing item from the source onto the target picture, because it was first time when I realized that the linear regression can be better than anything else, right? And it was after actually weeks of tries with other approaches, the only triangles and neural network approaches and so on, right? And then it turned out that, right, linear regression works. So it took a lot of time to prepare. Regarding data collections, as who was that? As Eva noted, yeah, it was a lot of work to manually label 9,000 pictures. However, it's rather simple labeling, okay, because it's easy to label whether somebody stands in front of the camera or sideways on in the back to the camera, right? So it was time consuming, but it wasn't as hard and as boring as usually labeling is, right? So yeah.
Cool. So I'll have another question for you from me. So I guess, well, you said that linear regression worked surprisingly well, but you mentioned that especially it was linear regression with cubic and quadratic features. So I guess that at the beginning you really tried the simple version of linear regression. Can you elaborate a little bit on how the simple version worked?
No, we couldn't use just linear regression, since linear regression is a linear projection, and we cannot use a linear projection. If you imagine, I'm not sure if I can share anything useful right now. In general, when you have two, let's say, masks of the source and target clothing item respectively, then you just cannot transfer the source mask onto the target masks linearly or in a fine way. I mean, linearly with some translations. It's just impossible. So we needed something nonlinear, but as close to the linear one as possible, right? And this was the goal. And the goal was achieved using just linear regression with nonlinear features, bonus features.
Okay, cool. So I have a follow-up question. Did you have any measure of how well the texturing actually works, or this was just done like visually?
It's a very, very good question and hard actually. We have some new results in the community channel. So if you want to take a look, then please do. Well, it works in a way. There are some steps which are pretty easy to measure, right? For example, how well the key points are transferred, or how well the key points are predicted. Transferred key points, right? This is just in the regression. You can just compute the distance between the transferred key points and the ground truth. So it's easy. However, there also are situations which are pretty hard to measure, to be honest. Let's start maybe with the typical problem. Then if you make a small mistake on shoulders, then it's very well visible. But if you make even a big mistake somewhere in here and around hips or something, then it doesn't matter, right? So there are, from the cognitive point of view, right, in the way as we see that, there are more or less important parts of clothing items actually, and it's pretty hard to transfer this impression into a measure of goodness of fit actually. So yeah, you're right that during, for example, choosing models, we often relied on our impressions, but it's somehow let's say reliable versions, since the final application is that you just take a photo of anything, anybody, and want to know how you look in the same clothing item, right? So your impression should be good, and this is the final goal of this project at the end of the day, right? So we had to decide somehow based on our impressions. Fortunately, we had both women and men in the project, so we could just talk about it. All right, we have several more examples. All right, the last example of Kacper is a typical example of situation when the model predicting the body part masks fails. And as you can see, the shoulders are predicted as being too low, which is very bad. And my impression from this picture is that it's just done badly. But and also there are some mistakes, as I said before, in somewhere in here. However, whatever I should call it in English, but they are less noticeable, right?
Okay, cool. So I guess that we've run up from all the questions. So we'll progress to the next presentation. Thank you, Patrick, for your very interesting talk.
Thank you very much. Once more, thank you for organizing this conference in such good way.
Thanks. It's really nice from you.